Okay, so I want to work the sixth problem on our review activity. In this problem, we're looking at a particle that goes around a corner. So let's draw something similar to what we had in the slides. So here's our particle, and it's coming around this corner, right? And the question asks if this particle that's coming around a corner will hit the wall. So we can imagine different trajectories of the particle as it comes around the wall. If it kind of swings too wide, then it will hit the wall. If it doesn't swing too wide, then it won't. A way to quantify this idea of swinging too wide is what we defined as a stopping distance. So stopping distance is the initial velocity of the particle times its relaxation time, v naught times tau. And if this stopping distance is, we'll call it x for now, if this stopping distance x is greater than the distance to the wall, then yes, the particle will hit the wall. And if its stopping distance is less than the distance to the wall, then it won't. And by distance to the wall in this case, I mean this separation here. Okay, so in fact this is fairly straightforward. We just need to calculate the stopping distance of the particle. So x is the initial velocity of the particle, which we're given as 5 meters per second. And tau, most generally, tau is the mass of the particle times the Cunningham correction factor over 3 pi mu dp. If we assume that we're looking at a spherical particle, then that simplifies to dp squared c sub c over 18 mu. So we'll use that bottom case. And since this is a 50 micron particle, then we don't need that Cunningham correction factor. It's hard to keep both of these on at the same time. So we're going to use the density of the particle times its diameter squared, converting the diameter to meters like I always do, and assuming that the Cunningham correction factor is 1. Then we divide that out by 18 times the viscosity of the fluid in which we're moving. So the problem should really explicitly say that we are in air, but for now we'll assume that we are in air at standard conditions. So then if we plug in all of these values, we get a stopping distance which is 0.0389 meters, or about 3.89 centimeters. And since we were initially given the separation of the wall to be 4 centimeters, then our stopping distance is less than the distance to the wall, and so no, the particle does not hit the wall.